Hey everyone, it's Lydia, and today we're going to be talking about some food science that is bringing Kernza perennial grain to the table. Now, if this is the first time you're hearing about Kernza, I would suggest taking a look at our first video that introduces it. But as a quick recap, Kernza is a grain that is harvested from a perennial plant, which means that farmers can plant it one time and then harvest it for multiple years. It also has a huge, nearly 10-foot long root system that is good for healthy soil, air, and water. But is it good to eat? Well, of course it is. Kernza is being domesticated specifically as a human food crop, and it's pretty tasty, with a flavor profile that's described as sweet and nutty. But if we want people to start eating Kernza, they need to know more than just what it tastes like. They have questions like, should I eat it as a whole grain? Or should I use it as flour and bake it into something? How much water should I add if I'm baking or cooking? What texture can I expect? All of these questions are what food scientists are trying to answer right now. One practical way to start answering these questions is to see what happens when we use Kernza to make the kinds of food that we're already eating every day. Since the plant that Kernza comes from is related to wheat, and since people are used to eating wheat products in the places where Kernza is being developed, a lot of early studies are about how to use Kernza in ways that we typically use wheat. For example, bread. Now, wheat is actually pretty unique compared to other grains, and these unique qualities have a significant impact on what we expect from foods that are traditionally made with wheat. And one of these unique qualities is gluten, and that's what we're going to spend most of our time on in the video. So, gluten is a substance created when you mix flour and water together to create dough. Only wheat and some of its closest relatives, such as barley and rye, create gluten. If you want to see what gluten looks like, you can extract it from a high-protein wheat flour. Just mix the flour with water to create dough, allow the dough to rest for a bit, and then gently wash it under running water. And then you can keep washing it, wash it a little bit longer, and keep washing it, and wash it again, until your water runs relatively clear. In this process, you're going to wash all or at least most of the starches out of the flour and be left with a ball of gluten. Now, this weird, stretchy substance is responsible for so many of the characteristics that we expect from our baked goods made from wheat. So if we want Kernza to live up to these standards, we have to understand if it has gluten, and if it does, if that gluten is similar to the gluten in wheat. So to do that, let's dig into what gluten actually is. Gluten is made up of proteins, specifically the proteins glutenin and gliadin. Proteins play an important role in all living organisms. The original function for the proteins that create gluten is to support germination and seedling development, which basically means that they're there to help baby plants grow from seeds. Proteins are macromolecules called polymers, which means they are large, complex molecules made up of a chain of smaller molecules. In the case of proteins, the smaller molecules that make them up are called amino acids. Now, even though these amino acids are linked together to create a protein, they still maintain their individual qualities, being attracted to or repelling other molecules around them. Because of this, when water is mixed with flour to create dough, the water molecules can form hydrogen bonds with amino acids that make up glutenin and gliadin. Now, these hydrogen bonds are not strong enough to create gluten, but they are strong enough to pull in the proteins and move them together so they can form a different type of bond called a disulfide bond. Both glutenin and gliadin contain an amino acid called cysteine, which can create a special bond called the disulfide bond with other cysteine molecules. These disulfide bonds are extremely strong, and as more and more of them form between glutenin and gliadin molecules, they transform into a giant mass of proteins called a cross-polymeric network. This network of proteins is what we call gluten, and its molecular structure gives it some really interesting properties. Now, if you made yourself a ball of gluten, you might have noticed these properties. For example, it's really stretchy, and if you throw it on the counter, it kind of bounces. But if you leave it there, which I forgot to do for this video, sorry, you'll see that it'll kind of melt into a puddle. This is because gluten has a special property called viscoelasticity. The visco part comes from viscosity, which is a term used to describe the property of liquids. And of course, the elasticity part comes from elasticity, which is a term used to describe the properties of solids. When you put them together, viscoelasticity refers to material property that is both liquid and solid characteristics, making it highly versatile and useful. It's a property that will allow it to stretch out without breaking and create chewy foods such as noodles, or stretch around air pockets and starches to make fluffy loaves of bread. If you have ever had to try and make a type of food that usually has gluten without it, you're probably very familiar with the importance of this viscoelastic property. Gluten-free breads, for example, tend to be much denser than bread made with wheat flour, and pizza doughs or pastas tend to be more crumbly and have less of a chewy texture. Now, you can get these viscoelastic properties from other ingredients to replace gluten, but it often takes a lot of work and can be challenging for a home cook. You might have also noticed that certain foods are easier to make with gluten-free ingredients, such as cakes or crackers, because they don't need to stretch or rise in order to create the textures that we're used to. Even when these foods are made with a wheat flour, they typically use a flour that has low protein, like a cake flour. Flour protein is measured in percentage, so a low protein flour, like a cake or pastry flour, will have around 7 to 9% protein, and a high protein flour will have 12 to 14% protein. And you can see an example of the differences in the images below. On the left is a loaf made with a low protein flour, which is much denser and softer than the one on the right, which is made with a high percentage protein flour, which has air pockets and a tougher crust. Now, coming back to Kernza, the nutritional analysis tells us that it contains a whole 17% protein, and we know that a large amount of this protein is coming from glutenin and gliadin. So based off of everything we know, that should mean that Kernza has a lot of stretchy gluten that will lend itself to the fluffy and chewy dough that we're used to getting from wheat flour. But that is not what happened. Let's take a look at these images from a baking trial. The image on the far left is 100% wheat, and then on the far right is 100% Kernza, with a gradient in between. As you can see, this is not what we would have expected based on the information we just learned about the protein percentage in Kernza. It looks like Kernza is acting more like a really low protein flour, or even a type of flour that doesn't have gluten at all. But we know that it has just as much, if not more, gluten proteins than wheat. So why are we getting this result? We know that Kernza has both glutenin and gliadin, but it turns out that the glutenin in Kernza has a key difference from the glutenin in wheat, and that difference is molecular weight. Molecular weight is exactly what it sounds like, the weight of a molecule. Now, a lot of simple molecules will have the same molecular weight no matter what, Water molecules are always going to be H2O, and they'll always have the same composition, and therefore the same molecular weight. However, more complex molecules, specifically polymers like gluten, might not always have the same molecular weight. This is because rather than having a specific chemical formula which is used to determine whether a protein is gluten or not, polymers are identified by the ratio and order of the smaller molecules that make them up. So one molecule of gluten might be made up of 2 or 3 times the amount of amino acids as another one, as long as they're in a particular order, and they would still both be called gluten. And that is the difference between the wheat gluten and the Kernza gluten. The gluten found in wheat has a higher molecular weight, which means it has more amino acids and is longer than the gluten found in Kernza. So, if you are watching this video as part of the lesson Cooking with Kernza in the Kernza in Context curriculum, now's the time for you to pause and get to work making your own models to explain why molecular weight would make this much of a difference in flour consistency. I'll show my own model and explain this in a second, but first, let's talk about what all this stuff we've learned about gluten means for making foods with Kernza. So is Kernza doomed to failure because it does not have strong gluten? Of course not. Rice and corn are some of the most important grains in the world, each of which has thousands of years of culture, recipes, and traditions built around them, and neither one of them has gluten. Of course, Kernza isn't entirely gluten-free either, so it's not suitable for people with a strong gluten intolerance, such as celiacs or an allergy to gluten. It's best to think of Kernza like some of wheat's other relatives, such as barley or rye, which both contain gluten proteins but are not able to form those strong cross-polymeric networks. These grains tend to be considered a bit healthier than wheat since they contain more nutrients, and due to having smaller molecule sizes, they're easier on the digestive systems of those with more mild gluten sensitivity. So using Kernza in ways that we use rye or barley, for example, as a whole grain in a salad or a porridge in oatmeal, or maybe we could use it for a really dense type of bread such as pumpernickel, might be a better idea than trying to throw it into wheat recipes. Another option would be to mix a smaller percentage of Kernza with wheat flour. Mixing 20% Kernza with 80% wheat can maintain the benefits of Kernza with its great flavor and benefits to the environment, while also allowing the gluten structures in wheat flour to do their thing to create a fluffy loaf of sourdough bread. There are so many delicious, nutritious foods that can be made with Kernza, and understanding what's going on at the molecular level is a huge help to bakers and cooks who are developing new recipes. Speaking of the molecular level, how are your models of Kernza gluten coming on? Let's take a look at mine. So on the far left, we can see uncooked long spaghetti noodles. These are representing the proteins and starches found inside of flour that has no gluten. They don't bind together at all, and you'd have to use a different binding agent to get them to stick together. In the middle, we have long cooked spaghetti noodles. These represent the gluten and gliadin molecules that are found in wheat gluten. As you can see, I can pick up just a few strands and they all tangle up together, forming a network. Finally, in the plate on the very right, we have short cooked spaghetti noodles. These represent the gluten found in Kernza. Now, there's the same amount of spaghetti on both plates, and they were cooked in the same pot, so they have the same level of stickiness. But as you can see, each individual short noodle has less connections to other noodles than the long noodles had. This is because it has less surface area and less opportunity to stick to more noodles. And because of this, the network as a whole is a lot less strong. Gluten is only one of the properties that food scientists, bakers, and home cooks are researching about Kernza. If you want to learn more about food science that's going on with Kernza, check out kernza.org or the Perennial Pantry website, which has published a lot of useful information about cooking with Kernza. If you're interested in diving deeper into any of the subjects from this video, you can check out the Cooking with Kernza lesson, and that has links to many of the resources that were used to create this information. If you're interested in learning more about other things about Kernza, you can check out other lessons in the Kernza in Context curriculum by checking it out on kernza.org. That's it for this lesson. Thanks for watching, and bye everyone.